All right, let's dive in. Today, we're going to break down the core ideas you absolutely need to know to crush those really tough Linux system programming interviews. Let's get right to it. You're in the interview. You've just sat down and boom, this question hits you. It's one of the most common openers, and honestly, how you answer this can set the tone for the entire interview. So how do you totally nail it? Well, it all starts right here. Processes and threads are, the fundamental building blocks of, pretty much everything in a modern operating system. Getting the difference isn't just trivia, it's the foundation of all system design. So here's the simplest way to think about it. A process is like its own separate house. It has its own unique street address, its own private memory, its own stuff. It's totally isolated. Threads, on the other hand, they're like all the people living inside that one house. They all share the same address, they can talk to each other super easily, and that makes them really lightweight and fast to create. But here's the real reason they asked this question. The interviewer isn't just checking if you memorize the definition. They're testing your design instincts. It's all about trade-offs. If you need rock-solid isolation, say for a web browser, where you don't want one bad tab to crash the whole thing, you'd use processes. But if you need pure speed, like a text editor that's spell-checking as you type, you'd go with threads. Okay, so that leads us to the next big problem. The best thing about threads, the fact that they share everything, is also their biggest weakness. Because when you have multiple threads all trying to grab the same thing at the exact same time, you get chaos. And that chaos has a name: the race condition. Seriously, this is one of the nastiest bugs to track down. Imagine two people are trying to update the last number in a shared bank account balance at the same time. One adds $100, the other withdraws $50. What's the final balance? Well, it completely depends on which operation finishes a nanosecond before the other. That total unpredictability? That's a race condition. So to stop this from happening, we have to identify the exact spot where the problem occurs. We call that the critical section. It's that specific little chunk of code where the shared data, the bank account, the file, whatever it is being read or changed. This is the danger zone.
So this brings up the million-dollar question, right? If we know exactly where the danger zone is, how do we actually, protect it? How do we put up guardrails?
We protect it using synchronization mechanisms. Think of these as the traffic cops of your code. They're the tools that enforce the rules of the road and make sure all your threads behave and access shared stuff in a nice, orderly way. And the two most famous traffic cops are the mutex and the semaphore. A mutex, which is short for mutual exclusion, is basically like a key to a single-person restroom. Only one thread can have the key at a time. It locks the door, does its business in the critical section, and then unlocks it on the way out. Everyone else has to wait in line. A semaphore is a little different. It's like a handful of keys to a restroom with multiple stalls. If you have 3 stalls, you have 3 keys. It controls access to a limited pool of resources, not just a single one. A really common interview problem brings this to life. They'll ask you to write a program where one thread prints even numbers and another prints odd numbers, but they have to stay in perfect sequence. You can't just let them run free. You have to use something like a mutex to force them to take turns. The even thread prints 4, passes the lock, then the odd thread grabs it, prints 5, passes it back, and so on. It's all about that controlled turn-by-turn coordination. Okay, so we've got threads covered, but what about those separate houses we talked about earlier? How do completely independent processes talk to each other? That's where inter-process communication, or IPC, comes into play. And Linux gives you a whole bunch of tools for this. You've got pipes, which are super simple, one-way data streams. Think of them as a conveyor belt. Then there are message queues, which are kind of like mailboxes, where processes can leave messages for one another. Shared memory is the fastest of them all. It's where two processes literally agree to share a chunk of physical RAM. And then you have sockets, the ultimate tool for talking to processes on different computers over a network. And yep, here we are again, back at trade-offs. An interviewer wants to see if you know which tool is right for the job. Do you need absolute maximum speed? Go with shared memory, but be really careful about race conditions. Need to talk to a server across the country? Sockets are your only real option. Your choice here says a lot about your practical engineering skills. All right, let's pull the camera back one last time and look at the most fundamental separation in the entire operating system. We're talking about the wall between your application and the OS kernel itself. So here's the deal. User space is where your programs live. Your web browser, your text editor, all of them. It's a protected sandbox with limited power. An app can't just decide to mess with the hardware or another program's memory. Kernel space, on the other hand, is the OS's playground.
It has full, unrestricted power to do anything. This separation is what keeps one buggy application from taking down your entire computer. It's a huge security feature.
So if your app is stuck in this limited user space, how does it do anything useful, like read a file from the hard drive? It has to ask the kernel for help. It does this using a system call. Think of it as the only official, secure doorway between the user space and the all-powerful kernel. And this happens through this really cool controlled dance. First, your app asks for a service. This triggers a special CPU instruction called a trap, which instantly flips the CPU from user mode into the super-privileged kernel mode. The kernel then checks the request, does the heavy lifting, gets the result, and then hands it back as the CPU flips right back to user mode. It's a beautiful, secure handoff of control. And here's a little pro tip for your interview. Don't forget to mention I/O control. It's like the Swiss Army knife of system calls. For all those weird, device-specific things that aren't a simple read or write, like ejecting a CD or changing your screen resolution, I/O control is the special catch-all call that handles it. Mentioning this shows you've gone a layer deeper. So, let's recap. This is your toolkit. We started with the basic units of work, processes and threads. We saw the big problem they cause, race conditions. We looked at the solutions, mutexes and semaphores. Then we saw how they communicate through IPC, and finally, the fundamental boundary they all operate within, user versus kernel space. Look, understanding these concepts is the key to understanding how our computers really work today. And it leaves us with a pretty exciting final thought. As our systems get more and more complex, what will be the new building blocks we'll have to master for the interviews of tomorrow?